again, we're going to just do positive integers. Okay, so P of x is going to be x as a prime number, and Q of x is going to be x as a perfect square. Okay, so first of all, we have to decide, is this a proposition or not? So there exists an x, Q of x. Are all the variables bound? Yes. Okay, yes, so it is a proposition. If it's a proposition, it has a truth value. So, okay, for an existential quantifier, remember, if I want to show that it's true, all I have to do is ask myself, can I find just one example of a positive integer that is a perfect square? Can we find one? 4. Okay, so there's lots of them, there's an infinite number of them, but sure. So, x equals 4 is an example. So this one is true. Just need one example to prove that an existential is true. Okay. On to the next one. For all x, Q of x, and not P of x, are all the variables bound? No, right? So remember, quantifier is done first, no parentheses in here, so this one over here, these logical operators are going to be done after, so this is free. Okay, so this is not a proposition. And since it's not a proposition, you know, we can't figure out, it doesn't have a truth value. Go to the next one. For all x, Q of x, or P of 3, are all the variables bound? Yeah. There's only one variable right here, and there's a quantifier right before it. This is bound, so this is a proposition. Okay. So we should be able to figure out the truth value of this. It has a truth value because it's a proposition. Okay, now the first thing we might want to do is go look at this part of it. So P of 3, so P of 3, okay, is that true or false? It's true, right? If I put 3 in here, 3 is prime. This is true. Okay. So, do I need to even think about this? No, why not? Because anything or true is true, and you might even remember the name of that law. Do you remember? What was it? Yeah, we use the law to do our short circuit execution, definitely. But do you remember the name of the law? Yeah.
The law of domination.
Yeah, it's a domination law. So this is true by domination. Like, the true is, you know, dominant over everything else, right? It trumps everything. Okay. So, yeah, we could go and try to, you know, maybe just for fun, is it true that for all x is a perfect square? Definitely not. Like, you can think of lots of numbers that aren't perfect square. But we don't even have to think about it, but, you know, just in case you wanted to know. Alright, next one. There exists an x, blah, blah, blah. Are all the variables bound? This time, yes, because of the parentheses. So the parentheses are there. So because of the parentheses, these are both bound. So this one is a proposition. Okay. So now we have to think, okay, so to make this one true, I just have to ask myself, can I find an x, remember x is from the positive integers, can I find a positive integer that is both a perfect square and a prime number? So is there a number that's both a perfect square and prime? Yeah.
1.
So 1 is maybe the only thing that you could think of. And now the question is, like, 1 is a perfect square, is 1 prime? No, it's not. I see Evan telling me, no, it's not. No, so 1 is not. So prime numbers have to have, you know, 2 factors, 1 in themselves. It can't be the same number. So prime numbers are 2 and larger. Okay. So the only possible candidate that we might be able to think of is 1, but 1 isn't prime. Okay. So, just let's make a little note here. 1 is not prime. Okay. And then all perfect squares greater than 1 are also not prime because clearly they have a factor other than themselves. So, does there exist a number that's both of these? No, there's no possible way for me to find them, so false. Okay, that one's a little tricky. Sometimes people think that 1 is prime, but it's not. Alright, and then the last one for all x, okay, the number is not a perfect square or it's prime. Is it true that every single number is either not a perfect square or prime? Alright, Evan's saying no. Can you think of an example? So if we want to prove that a universal quantifier is false, we just need an example. Can you give me an example?
9.
9. Okay, so let's do when x is 9. Okay, let's see what not q of 9 or p of 9 would be. Okay, so q of 9, x is a perfect square. Well, 9 is a perfect square, that's true, so this would be not true. Or, and then p of 9 would be p is prime. Okay, well 9 is definitely not prime, that's false. Oops. And so we have false or false, which is false. So sure enough, he found a counterexample. So remember, for a universal quantifier, if I just find one counterexample, that's enough to show it's false. So this one is false. So hopefully all these examples are driving home the point that if I want to prove that an existential is true, one example. If I want to show that a universal is false, one counterexample. Okay, a lot more argumentation has to go into trying to prove that something like an existential is false. I have to kind of consider every single one of them. Okay. Alright. So, we've looked at it with, numbers and just small statements. Let's try translating these English statements into terminology, into logic statements, because that sometimes can be tricky. Okay. Alright, so let's say we have the domain of these predicates that we're going to define as a set of all students at a university. If you want to think of it, it can be at Tennessee Tech. Okay, and so E of x will be that the student that we're considering is enrolled in the class, whatever class we're thinking about, maybe it's our class, and then T of x would be the predicate for that person took the test. Okay, so we want to translate statements from English into logic. Like usually if you can get them into logic, they're much more easy to work with. Okay, so when you look at the word someone, you should ask yourself, does that seem like an existential or a universal quantifier?
Universal.
Okay, so universal, you're going to change your answer?
Yeah.
Yeah, that seems like existential, right? There's just somebody. There exists, at least one person is someone. Okay, so that word someone, indicates to us we're talking about existential. Okay, so we're going to do there exists an X. Okay. And then if I were you, I would just put parentheses, because there's something about being enrolled, something about taking a test. We're going to have to include both of those, and it's probably going to involve some kind of logic operator, so you better just put parentheses there, otherwise you might forget them. So just put your parentheses there ahead of time. Okay. So how can we express the idea that there exists a person that's enrolled in the class and they took the test? Yep.
E of X and T of X.
Yeah, E of X and T of X. Good. Okay. So there exists a person that is enrolled in the class and they took the test. Okay. So one thing to note, okay, it is not, okay, there exists an X such that E of X implies T of X. So sometimes it's tempting to think that it's that instead. To say, there exists a person that if they were enrolled in the class, they took the test. Kind of feels like maybe it could be alright. Okay, but let's talk about why that's not correct. Okay, so we're talking about all of the students at a university. Okay, and so I could find a student that's not enrolled in this class. Okay, so E of X would be false, and false implies anything is true, right? False implies false is true, false implies true is true. It doesn't matter what the anything is. So I could find a person that's not enrolled in the class to make this true, and it might be the case that every single person enrolled in the class didn't take it, but I can still find a student that is not enrolled in the class that would make this true. So I could make this true by using a person that's not enrolled in the class. And is that the idea we were trying to get across here? No, we were trying to get across the idea that there's someone who really is enrolled in the class that took the test. So this is not going to work. Okay, so I can make this true with a person, a student not enrolled in class. Okay, so it's not going to give me the same kind of truth value. It's very important that you use the and here and not the implication. Okay, so let's go to the next one. All students enrolled in the class took the test. When you see all students, hopefully this triggers, like, I know what kind of quantifier I'm going to use. What are you going to use? Universal, definitely. This is definitely going to be a universal. Okay, so we're going to do for all X. Okay, and once again, we're talking about multiple predicates up here being enrolled, taking the test. You better just put your parentheses in there so that you don't forget them. Okay. And this is it's very similar to the previous one. So, here's the question. Should I put the same thing? All students are enrolled in the class and took the test. Okay, is that what this is saying? That every single student in the university took the test? That's not actually what it's saying, but if that's what I write here, the only way for it to be true is if every person in the domain took the test. So this one is not going to be the same thing. This time, this is the one that works. So the E of X implies T of X. Okay. So notice that for every student that's not enrolled in the class, this will be false, and it'll be true for all of them. So that handles all the people that are not enrolled in the class. It's going to be true for all of them. Okay. And then the only way for it to be true for the people that are in the class is if they took the test if they were enrolled in the class and they took the test. There can't be a false conclusion right here, right? And so this statement will be true for every single student in the entire university. Okay. Can you wrap your brain around that one? Okay, so it's true for everyone in the class because if they took the test at least. Okay, so if all the students took the test, this will be true, this will be true, all of them have true implies true for the people that are in the class, but then it also has to be true for everyone in the domain. It has to be true for everyone in the entire university. So all those other people that aren't enrolled in the class all have false implies, probably false, because why would they come take the test if they weren't enrolled, right? But still, false implies false is true for all of them. So this statement will evaluate to true for every single person in the university. So this one will be true. Now if I made that an and, it wouldn't be true for everybody in the university. So once I put that universal there, I have to change that to an implication. Okay. So that's a little bit tricky, right? So if I'm using existential, it's got to be an and, or it's not going to be correct. If it's universal, it's got to be implication, or it's not going to be correct. Okay. Let's try the next one. Everyone who took the test is enrolled in the class. You see the word everyone. What kind of quantifier?
Universal.
Definitely universal. So definitely universal. I'm going to stick in my parentheses so I don't forget them. Okay. So, do you think we should be using an and or an implication? We're going to have to use implication, right? This is a universal. We better use implication. Okay, so what implies what on this one? What's the hypothesis?
G of X implies G of X.
Yep. If they took the test, then they're enrolled in the class. Okay. And then the last one, at least one student who was enrolled in the class did not take the test. So when I see at least one student, what kind of, should be telling me it's what kind of a quantifier? Existential, that's right. Okay, so if I have existential, okay, what kind of logical operator is going to be used in here? It's going to be an and, definitely going to be an and. Okay, so what should I and together? Go ahead, Vaughn, tell me.
Students in the class, but not the test.
Okay, so what's up here?
So E on one side and then not T on the other.
Yes. Good. Okay. Yes, so notice, it's very important that when I have existential, you're going to be using conjunction, using an and. When I have universal, you're going to be using implication. Okay, and it won't give the same truth value if you don't write them that way, so we have to be very meticulous and careful about those. Okay. All right. So, we have these quantified statements, and De Morgan shows up again. So we can use De Morgan to write the negation of quantified statements. Okay, so we'll start out by looking at an English example, and then we'll just go to all symbols. Okay, so if you have a quantified statement, you can write the negation, it's a proposition, and you can write the negation of that proposition. And sometimes in English, when you're trying to negate a statement, it gets a little bit strange, like you reword things when you negate them. Okay, so let's say we've got students in the university, this time it's students in the class, so, and we've got Q of X has took the quiz and F of X has failed the test. Maybe they should have been both test or both quiz. Alright, it doesn't matter. Okay, so let's say I have this, not for all X, Q of X. Okay, so if you think about this, the order in which the operations, the universal is first. So, okay, that, everything is quantified, that's a proposition, and after I evaluated that, then I would change, like the not would happen last. Okay, so it's definitely a proposition. Okay, think about how you might state that in English. Not for all X, Q of X. Alright, go ahead, Sam.
For nobody delivering? Sorry, I'm late.
Yeah, well, so nobody gives me the idea that it's not a single person. And is that the same idea as, so not everyone and not a single person, are those the same ideas? No. So we have to be really careful about that, because nobody makes me seem like there wasn't a single person for which this was true, where this is just saying not everyone, right? And that's a little bit different. So, like, good idea, but I think maybe we need to do something slightly different. So, how might we word this? Okay, Matthew, what is it?
Not everyone took the quiz.
Yeah, so not everyone took the quiz. Okay. But just the fact that we have the discussion means that this is kind of a confusing statement, isn't it? Okay, because we're trying to decide, should I have said nobody or not everyone? This is not everyone. Like, what's another way to say not everyone took the quiz that's like a little bit more clear to us? Yeah.
Not all the students in the
class took the quiz?
Yeah, that sounds like it's not everyone. Yeah, what do you think?
At least one of the students didn't take the quiz.
Yeah, so at least one student didn't take the quiz. Okay, or you might even say at least one student, you might get that idea as someone didn't take the quiz. Okay. And at least in terms of English, that's a lot easier for us to understand than saying, not everyone, like, and you're like, what is that? But here, someone didn't take the quiz, that's pretty clear to all of us. Okay, so someone didn't take the quiz, how would we write that as a logic statement? So, there exists, good, so there exists an X. And then what would come after that? Yeah, not Q of X. And I'll put that in. Okay. Okay. Alright, so notice that these two, okay, are equivalent. They're saying the same thing. This one is just a little bit easier for us to understand, but this one right here and this one right here are exactly the same. Okay. Let's try the other. So, well, let's try, one instead of with a universal, if we have a existential. So if I do not there exists an X, f of X, how would you say that one in English? You have an idea, Victor?
I don't know. I was going to say, is it nobody?
Austin, what's your idea? So, say that again? Okay, so is this saying nobody? Yeah, well, yeah, when we reword it, that's why, because let's just take this one and just try to take this exactly into English. This is, so I think you're doing the equivalent. This one is equivalent. Like, how would I write this in English though with this? Then we'll do the equivalent, because I think you're onto that. Yes, you're right. But let's do this one first. All right, go ahead, Grant. Matthew helps us a lot.
Someone did not fail the test?
Okay. Not quite.
Not one that failed the test.
Matthew, what do you think?
Not a single person failed the test.
Yeah, so okay. And then, there does not exist a person that failed the test. It's like, right, so not a single person failed the test. That's right, the right idea. Okay, and then Austin, what were you going to say? Like, this is much easier to understand if I say what? Everybody. Or let's put it with everybody. So everybody then. Everybody passed the test. Like, that's much easier for us to understand. And hopefully that will always happen, right? So it's much easier for us to understand everybody passed the test. Okay, and so if we have to write that as a logical statement, okay, everybody, that's for all X, and how do you express the idea of pass the test? Using just what's up here. Yeah, not f of X. Okay, so notice that these ones, so this one right here, and this one right here are equivalent. Now we're talking about this was like the Morgan for quantified statements, and so look what happened in this one. This negation moved past the universal quantifier and went in front of the Q of X, and it changed this to there exists. Over here, this quantifier moved past the existential quantifier in front of f of x, and the existential turned into a universal. So it's very similar to what we saw in De Morgan, where when the negation moved into the parentheses, it changed the, negated the predicates and then changed the conjunctions to disjunctions, the disjunction to conjunction. So it's a very similar kind of idea. Okay, so let's see why we're calling this De Morgan. Okay, so here's the laws, De Morgan's laws for quantified statements. They are what we just figured out they would be. If I move the negation over a quantifier, it will change to the other quantifier. So universal changes into existential, existential change into universal. Okay, but why are we calling this De Morgan? So let's think about it. So let's say I have for all x, p of x. Okay, so this is true. When you think about what that means, this means that for every single x in the domain, p of x is true, right? It has to be true. So if I logically wrote this out for everything in the domain, this would be like p of x1 and p of x2 and p of x3, and on it goes, and I would AND all these together until I exhausted everything in the domain. But I have to AND them all together. The only way for the universal to be true is if every single thing in the entire domain is true. Okay, so imagine now I negate this. So if I negate, maybe I'll do this in a different color so you can see, like that's the original. Okay, now if I go and I negate this, okay, well then I would have to be negating this, and think about what happens. Well, now I've got this logical statement. This turns into not p of x1, and now De Morgan says that's going to change to an or, not p of x2, or not p of x3, or on and on it goes, not p of xn. Okay. And so if I'm saying this or this or this or this, the way for this to be true is if I can just find one example for it to be true. So we're always talking about the existential quantifier, right? So this is the same thing as there exists at least one x. It's either this one or this one or this one or at least one of them. And as long as one of them is true, this will be true, right? So these are, whoops, there should have been a not in front of that, right? So at least one of these has to be true. So these are exactly the same. I'm just thinking about how in a universal, it's actually ANDed together. And so when I negate that, all of those turns to ors. Well, or is really the existential quantifier. Similar, if I have there exists an x such that p of x, that's the same thing. Okay, I only have to find one. It could be the first one that's true, or it could be the second one that's true, or it could be the third one that's true. On and on it goes. I only have to find one of those to be true for this one to be true. So of course when I negate it, I have to negate all of that, and now De Morgan is applied. So I'm going to get not p of x1, and that turns to an and, not p of x2, and all of these turns to ands. Okay, and if I'm anding them all together, the only way for this to be true is if every single one of these is true. So that means that for every single x in the entire domain, not p of x has to be true. Right, so those are the same thing. So you might feel like, oh, well, De Morgan only applies to ands and ors. Like, it's still applying to ands and ors, but that's how the ands and ors are related to these quantifiers. Okay. Does that make sense? Questions about that? Good? Okay. Okay, and so now that we have De Morgan's laws, we should be able to, you guys get that? Do you still need it? Okay, I'll try. Okay. So let's say we had an expression and we wanted to rewrite the expression so that we can obtain an equivalent one, okay, where the negation applies to a predicate rather than to a quantifier, because often it's easier for us to deal with a negated predicate than a negated quantifier. Okay, so if we're going to take this and we're going to move it over in front of the predicate, okay, this is going to become, okay, so when I move it past the existential quantifier, what happens? It turns into a universal, right? So when it goes over there, this is going to turn into a universal, and then the negation is going to come in front of there. Okay. And you don't necessarily have to put the parentheses in front of the negation, because that's right after that, and you can't negate without, but if you, sometimes it just can't hurt to put parentheses, so I like to put the parentheses there anyways. Okay, so with this one, okay, we're going to take the negation, we're just going to do this one step at a time, we're going to move it across there, and when we move it across, this one's going to change. So this is going to turn into for all x, and the not is going to come in front of that whole thing. Okay. Now the directions were, and you have something like this in your homework when you do it, so this will help you out with that. Oh, this is rolling away. Okay. I won't lean on it too hard. Okay, so now it says we want a negation to apply directly to a predicate. Okay, so right now this is not applying directly to a predicate, it's applying to a logical disjunction of predicates. So we need to apply De Morgan again. Okay. Again, I want to put parentheses around it. And when I apply De Morgan to this, okay, now we're going back to logic. You know, not for universal quantifiers, for quantified statements, but just for a disjunction. For a disjunction. So that will turn into not P of x, and then the disjunction turns into conjunction, and not Q of x. There. And now, we have every negation applies directly to a predicate. This negation, directly to a predicate. This negation, directly to a predicate. Alright. The next one, we'll do it again, one step at a time. So we're going to move this one across the universal quantifier, and it's going to change that one into existential. So this is going to become there exists, and the negation is going to go over there. We'll just leave the P of x and Q of x. And now we want to make sure that the negation is applying directly to a predicate. It's not like that now, so we've got to do one more step. I know that some of you could do this all in one, but we're going to do it in two so everybody can see. Okay. So we're going to apply De Morgan to this one. We'll do not, the first one. And then the conjunction has to change to disjunction, and then not Q of x. And there's a lot more going on in this last one, so I would definitely, do this one in a couple of steps if I were here. So the negation is going to move across, so that's going to turn into existential. We'll have a negation in front of this whole big thing. Oh, lots of parentheses. So leave this one alone. And now when we apply De Morgan's here, okay, this is a conjunction of two things. Okay, so think of it that way. I need lots of parentheses. So I'm going to do not the first thing, change the conjunction to a disjunction, and then not the second thing involving the conjunction. And that's that thing in the parentheses. So this is Q of x or R of x. And now, do we have every negation applying directly to a predicate? Well, this negation applies directly to a predicate, but this one doesn't. Okay, so we need to keep going. So this one's fine. Okay. But this one, we need to apply De Morgan again. And this is going to turn into, and I'll just go ahead and put parentheses, this is going to be not, and then Q of x, and then this will change into an and then not R of x. Okay. a good question is, do I need this set of parentheses here? But technically no, because if I took them away, conjunction has higher precedence than disjunction, and so the order of operations would say I need to do it. But is it really helpful to have the parentheses there so we remember, there's nothing wrong with leaving the parentheses there so that we all remember, oh yeah, conjunction would happen first anyways, but just let's leave the parentheses there so it's very clear and we all know that that's the thing that's happening first. Okay. So I know that's like busy with lots of parentheses. I'm sure you've written computer programs where you have to put bunches of parentheses on. Just too bad we don't have an editor that will tell us whether they match or not. Okay, so in this one we're going to use laws of, so De Morgan's law for quantified statements and laws of propositional logic to show the logical equivalence between these two sides. So this is some good practice for us. Okay, so once again, if I'm trying to show a logical equivalence, I can just start with the left side and apply laws that I know and try to transform it into the right side. Okay, so I'm just starting with this. Okay, I see that there's a negation in front of a quantifier, so the very first thing that I want to do is probably apply De Morgan's law for quantified statements. So I'm going to move the negation inside, and that's going to become there exists X, and I'm going to put a not in front of the whole thing in parentheses. Okay, and so this would be De Morgan's law for quantified statements. I'll just abbreviate it. Okay. Okay, so looking at that, alright, we've got there exists an X, that matches, but when I look at the expression here, it's not exactly the same as this. So, what should we do next? Just apply De Morgan's law, so I'll leave this the same, and then I apply De Morgan's law, that's going to go inside the parentheses and negate the first, change the conjunction to disjunction and negate the second. I just did plain old De Morgan, and if you want to put De Morgan logical, that's okay. Now it looks really close, there exists an X, the not P of X matches up, the OR matches up, the only thing that's different is these, so what obviously should I use here? Yeah, double negation. Okay. Alright, let's try this one over here. So when I see this one out in front of the quantifier, of course the first thing I'm going to do is De Morgan's for quantified. I'm going to turn this into existential and put the negation on the other side. Okay. And then I notice that there's an implication in this one, but what I'm trying to get it to be, this doesn't have an implication in it. So what do you feel like you want to do? And an option is not like run away and cry. You have to do something else. What law do you want to apply? Yeah, say it. What was it, Evan? Yeah, the implication law. Alright, so, like I don't have my cheat sheet, so I hope that, does anybody remember what the implication law is? I think I have my, this one. I have my shape version. So, when I have square implies circle, it becomes not square or circle. So it's not the first thing or the second thing. Okay, so I have that version handy. Okay, so when I apply that law, okay, I'm only applying it to the first one. So remember, it becomes not the hypothesis, so not P of X, that's the hypothesis, or the the conclusion. So there's our Q of X. So there we applied the implication law. Okay. What seems like an obvious thing to do next? Double negation. Yeah. Now whenever you see that, you're just like, whoa, too many. Let's get rid of it. So that becomes P of X or Q of X. Okay. And we're almost there. What should we apply last? De Morgan. Yeah, so we're going to do De Morgan. So when we take the negation inside the parentheses, they'll become not P of X. The disjunction changes to conjunction. We got to not both of the individual predicates. All right. So that is De Morgan for quantified statements. It feels, pretty similar to what we did with De Morgan for logical statements, so it's not too difficult. Good. Yes.
On tests and stuff, do we really need to write out the double negation?
You should write out the double negation on the test. Yes.
We have to write down what law that is.
Yes. Yes. So you should write out. Like if you want to do it in one step, okay, if let's say you want to go from here, from here to here, okay, then you just need to list two laws in one step. So you'll just say, double negation De Morgan, and just put them together. So if you do two in one, that's fine, but if you use double negation to replace that, there's a reason that you got rid of that, right? And so, you can list more than one step if you'd like to. I'm listing them out one at a time, so I know some of you are like, it'll kill me now. But, yeah, so, yes, if you use more than one, then list more than one. Yeah. So that's fine as long as you list every law that went into making those replacements. If you use two in one step, list them both, yes.
What if I just have every single step without remembering the name of the law?
Then you will not get credit for it. Yeah. The whole point of the question would be to show how you use the laws.
I just know what it is. I don't know what it's called.
Well, it's important for you to know what it's called. Yeah. So now I'm gonna give you the laws, and then you just look at the piece of paper and go, oh, what law did I use? And you write it down. It's like you should be able to recognize what law you're using, right? So. Yeah, I'm giving you the laws. I'll give you a piece of paper and all the laws will be listed there. But you have to, yes, I will give them to you. I will realize this. I will give you the laws. I'll tell you what they say. I'll tell you their name. But when you go and write something, you have to recognize what law you're using and tell me what law it is. Yeah. That's a skill that you should have. You should know what law you're applying. Okay. All right. Let's see. Let's go ahead and stop there because we're probably not going to get through all of 1.9, so we'll just stop there. We will look at start from 1.9 next time. So remember that you've got homework up through section 1.8 due before class next time. You should have probably also taken a look at the study guide, so just in case if there's any questions that you have about it, you can ask them because that's the last opportunity to ask me about it before your test.